Welcome to the first lecture, and we start off with the number systems, which is the chapter 1 in CBSE 9 mathematics. So going forward, I will be naming every lecture in the format 9.MATH.A1. So 9 represents the 9th standard, math represents that it is a mathematics lecture, and A means the version, and first is the video number. So the next video will be 9.math.A2. So now we will proceed with the subject. So in number systems, the first thing that we are learning is what is a number line and what are the different types of numbers that we are going to encounter from now on, that is from class 9 to higher up. And how do we represent these various types of numbers on a number line, and in general what are these types of numbers, or what are the different ways we can classify numbers which can help us in future. So let us look at what is a number line. It is simply a line, and we divide the line at specific points, as you can see here, and we designate with the numbers. I know very well that all of you have a very good understanding of what is a number line. You just have to take a scale and look at it. On a scale, we have numbers printed, and these numbers are printed at specific intervals, right? Typically, most of the scales, let's say a 15 centimeter scales, have numbering from 0 to 15, and each of the numbers are printed at specific points. Parallelly, you also have one more number line on the other side of the scale, which is in inches. So we have two examples of number line representing numbers at different set of intervals. And so what you see on a scale is exactly what a number line is used for, to represent numbers and using that to quantify things. Irrespective of the units, be it centimeter or inches, what we have to ensure is that the distance from 0 to 1 should be same as 1 to 2 and should be same as 2 to 3 and so on. So before we go in detail about learning into what are number systems, I think we can take a moment and try to understand how this knowledge has come into existence. I don't know the location, but looks like a modern city. You can see the skyline, and if I represent our current year in a number line, we can do something like this. So we have 2019, 2021, and we are somewhere here in 2025. And what are we doing? We are learning number systems in class 9. Okay, so you don't have much choice here. We are here to learn. Let us look at how mathematics or number systems, which is a kind of building block of the overall mathematics, has come into the form that we see today. Now mathematics has evolved, okay, or numbers have evolved gradually with how the human cognition, how the language and how the culture has evolved. As the humans progressed through their language, culture, how they improved their standard of living, mathematics also has, gained popularity within the society and also has grown in complexity, so that we are now at a stage, we can design a lot of things the way we want because of the underlying mathematics in it. Now when we look long back into our history, let's say we go to the time span of minus 50,000 BC to around minus 20,000 BC, you can see it is a negative number, so going forward in time from left to right. Okay, so let us look at what people would have done during these times. So what you can see here is some beach, if you can say, and there are stones all of the beach, and maybe someone would have taken one stone and started scribbling. And what we have is early concept of numbers. Maybe someone would have started counting the number of stones. They would have realized that counting the number of grains is a much harder task. Maybe counting stones is better, but nevertheless, people might have introduced, or they might have gotten a very good stone and they have started to note some marks on it to indicate some counting symbols. So that's what we can see. If you actually look into the history, you will see stone plates and with some certain symbols representing certain numbers. So this was the way people try to represent quantities physically. So let's say we proceed further in time to a time span of around minus 5000 BC to minus 10,000 BC. We can see we as a humans have started to count numbers, and numbers were mostly objects. Imagine a market, during this time. They might have used some objects, maybe apples or carrots, what was popular or easily available as objects, which could be used as to count or to as a reference in the barter system that people might have used to trade. I don't know the exact history, but kind of understand that this is the way people would have progressed in time. Now if we come even closer to 2025, around minus 4000 to minus 2000 BC, this is where kind of mathematics became even more complex, or we can say the kind of mathematics that we see today, it started around this time frame. So we can call it the birth of mathematics, and more usage of symbols. Of course, this was not unified all across the world. Each culture had certain symbols which they used to represent numbers, and so we had the Sumerians, Egyptians, people in Indus Valley, Chinese, all actively working in mathematics in some form. And what you can see is a kind of example of how Egyptians represented numbers. So this is a cartoonish image just to represent or have an idea about how numbers was represented. Much more complex than the numbers that we have today, that is 1 2 3, and the kind of shape we have assigned to each numbers. Let's go even further in time to around minus 600 BC to minus 300 BC, and then what we have is the birth of modern mathematics. So much more complex in terms of how numbers could be manipulated or used to help us in real life. So we had Pythagoras, Indians, Babylonians, all contributing to the modern mathematics. And it is in this time we have negative, zero, rational, irrational numbers introduced into mathematics. In this particular chapter, that is chapter 1 of CBSE 9 mathematics, we start off with number systems, and what you can see here, that is zero, negative numbers, rational numbers, irrational numbers, form the basis of the first chapter, and we are going to learn all these things in detail. Let us have a relook into how these numbers would have evolved, and through this way let us try to understand how different kinds of numbers can be categorized. Okay, so let us look at a very common example or a common object that we all are familiar with, an apple. Okay, so how, let's say we have to represent an apple on a number line. So figuratively, how can we do it? Let's say we have just one apple and we put that apple in a bucket, as you can see here. So in one bucket we have only one apple, and let's say we have a second bucket and we have two apples. Similarly, we have three apples in a different basket, and we have four apples in a different basket. Okay, basket or a bucket. So as an image we can try to represent all these things above a number line, let's say, and we all know by symbols we represent by 1 2 3 4. It is now good to take a moment and try to understand what would have been a world without numbers, or the concept of numbers as we see today. Imagine a conversation between a shopkeeper and a person who have come to buy apples. Let's say the person wants to buy 10 apples. How he would have communicated that he needs 10 apples to the shopkeeper? There is no concept of 10, right? 10 is not there in those times. So perhaps he might have told he needs apple, 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 apple 10 times, so that the shopkeeper would have understand, okay, this person needs 10 apples. He might have to tell apple 10 times to get this information conveyed from the person to the shopkeeper. Or maybe if the shopkeeper was a little bit more user friendly, he might have drawn a chart of apples in different baskets, and the person can just point to the bucket having 10 apples, and the shopkeeper might have understand. But it is not easy, right? You cannot imagine those kind of lifestyle today, or we may not even spend time to think how life has become easy with the introduction of numbers. We just say number, we just say I need 10 apples, or we say maybe 1 kg of apples. That's how numbers actually help us in real life. So numbers, if you look at from a different perspective, numbers are basically a shortcut that is created by humans to simplify communication, right? If there was no numbers in the language that humans use, life would have been much tougher in dealing with people to people or in trade, communication. So these numbers like 1, 2, 3, 4, with which we can count objects, is what we generally refer to as natural numbers. So this has naturally come into the life of humans because we usually start counting from 1, 2, 3, 4, and we can go on counting all the way up till infinity. So there is no end to it. So there are infinite natural numbers that we can look into. So whenever we want to count, we usually start from 1 and go on, and those numbers are referred to as natural numbers. But again, when people proceeded, or as time evolved, people would have realized there is no object or number to represent nothingness, right? If we have to represent nothingness or emptiness, how do we represent it? Well, that's how this concept of zero would have come, representing, let's say, an empty basket. And now with the inclusion of zero, we can say now with the inclusion of zero, we can improve the classification of numbers to what we call as whole numbers. Okay, so whole numbers are basically natural numbers plus 0. So with 0 included and all the natural numbers together or in complete or in whole, we refer to as whole numbers. Again, there are infinite whole numbers. Moving further, again people would have thought that okay, we have now figured out all kinds of numbers that are required to represent all kinds of scenarios in life, until someone who has started a bank, or there was a money lender who wanted to give money for an interest and make money out of it. But then how he would have represented his dealings, right? If a money lender is giving money to a certain person, let's say person A, let's say he is giving 100 rupees, how the moneylender can note this down on his accounting book? He can say he has lent 100 rupees to a person A, and he can actually write it down as minus 100, right? Because he is now devoid of minus 100 rupees. Or it could be from people to people. One person is giving money to another person. So the first person is now short of money and the other person has gained money. So one is having shortage, we can represent it by negative numbers, and one who have gained, we can represent as positive numbers. So if we continue the images of apples into negative numbers, maybe I can put it something like this, numbers on the other side of number line. So this is just to understand figuratively. Of course, in real life, we don't use apples to denote numbers or objects on a number line, but just for all of you to understand. And negative numbers we can put with a negative symbol just before the numerals. So we have -1, -2, -3, -4, and so on. So these numbers is what we refer to as integers. It goes all the way from negative infinity, -4, -3, -2, -1, 0, 1, 2, 3, and again all the way to the positive infinity. So again there are infinite integers available for us, and maybe people would have thought that okay, now with the inclusion of negative numbers, we are now successful in defining or creating numbers to explain all kinds of scenarios in life until somebody would have started to share an apple, right? Now what if someone has to share an apple? What kind of numbers are required to explain a sharing scenario? Let us look at few apples which are complete in nature. So we have one full apple, and for now we have put it below the number line, so it is a negative number. We have two full apples and it is a positive number. Now let us look at this case. We have half of an apple. Now how do we represent it? So it is 1/2, so we can represent it as 1 by 2, and on a number line it should be between 1, 0 and 1, right? Because it is not an empty apple or it is not one full apple, so it has to become between 0 and 1. Let us look at one more example. We have 3 full apples and 1/2 of an apple. So it is 3 full apples and 1/2 of an apple. So we will be writing it as 3 plus 1 by 2, right? So 3 plus 1 by 2, if you compute, you will get 7 by 2. And that is a value between 3 and 4, right? 3 will represent 3 full apples, and if we had 4, then we would be representing it here. So it is a value between 3 and 4. So on a number line, it will be exactly between 3 and 4. Of course, 3 and 4 I have not shown here, but you can take a moment and try to understand it. We will look one more example. Let's say we have 2 full apples and 3/4 of an apple, right? I have removed 1/4 of an apple, so remaining 3/4 of an apple is with us. Now how do you represent it? It will be 2 full apples plus 3/4 of an apple, or 2 plus 3 by 4, and if you compute, it will come to minus 11 by 4. So minus 11 by 4 will be a quantity between 2 and 3, right? It will be a quantity between -2 and -3, to be specific. Altogether, if I represent all these numbers, we end up with what is called as rational numbers. So it includes all the natural numbers, it includes the whole number because 0 is now part of it, it includes all the integers, right, because we have negative numbers, and further we have now decimal numbers, right, or numbers in represented as ratios, and it can be both negative or positive. So let's say minus 11 by 4 is a value between -3 and -2, 1 by 2 is a value between 0 and 1, 7 by 2 is a value between 3 and 4. All these numbers together is what referred as rational numbers. Okay, we now take a kind of break before we further add more complexity to what we have studied now. We will go a bit more deep into how these numbers behave. Okay, so it is good to have a quick revision of what we have studied till now. We have natural numbers. It goes from 1, 2, 3, 4 all the way up till infinity. These are basically numbers that humans have naturally used to count objects in daily life, but there was no number to represent nothingness. Then we have introduced 0. So with 0 included, we have whole counting numbers including nothing. So whole numbers represented by W. We have numbers going from 0, 1, 2, 3 all the way up till positive infinity. Further, we realized that we need more kinds of numbers to represent in the case when we are going to lend some money or lend some apples to someone. So then we have negative numbers. If you combine negative numbers with the whole numbers, okay, we have integers. Again, there are an infinite number of integers, there are an infinite numbers of whole numbers, and there are an infinite amount of natural numbers. Okay, so integers are complete units like whole numbers. So integers are complete units just like whole numbers. So it is like -2, 2, -3, -4, but we also allow them to be negative. It is same like whole numbers, but we also allow them to be negative. But the point to be noted here is they do not have any fractional or decimal parts. So we don't count, let's say 1.2 as a integer. Let's see another example, 4.3. 4.3 is not considered as an integer. Okay, it is not an integer. Another example, let's say there are minus 5 here, minus 5 by 2. Minus 5 by 2 is not considered as an integer. For that we will introduce something, right? Therefore, for that we have rational numbers. So rational numbers are a further addition to integers, where we include these ratios or decimal numbers. So a number r, a number r is called a rational number when we call it as a rational number if it can be expressed as a fraction p by q, where both p and q are integers and q is not equal to 0. So what actually this does it mean? Okay, so in other words, any number from the collection of rational numbers can be expressed as a ratio p by q, where both p and q are integers and q is not 0. So any number from the collection of rational numbers. So you take any number from this collection of numbers called rational numbers, we can express it in the form of p by q or p divided by q. There are two conditions that we have to satisfy. Both p and q have to be integers. The second condition is q should not be 0. Okay, so we will look at few examples. Let's say the first example of a number 37. So 37, is it a natural number? Yes. Is it a whole number? Again, yes. Is it a integer? Yes. Now, is it a rational number? So 37 we can represent as a p by q. How? If we take p as 37 and q as 1, okay, then it follows all the laws pertaining to rational numbers. So p is 37, q is 1, and q equal to 1, which is the denominator, is not equal to 0. So 37 can be represented as a rational number. So any number, a number r is called a rational number if it can be expressed as a fraction p by q, where both p and q are integers and q is not equal to 0. So visually, let us see how we can classify or represent all these numbers whole together, not in a number line. Of course, we can represent all these numbers in a number line, but we'll try to see it from a different perspective. So natural numbers are numbers which are generally used by people to count 1, 2, 3, 4 and so on. So what I have shown here are just 4 examples, and when we include 0, we have the whole number represented by the letter W. Natural numbers are represented by the letter N. So any number within this box is a whole number. So 1 is a whole number, 222 is a whole number, 1,54,000 is a whole number, and so is 0. 0 is also a whole number. So further, if you proceed, if we include all the negative numbers, we have what we call it as integers represented by the letter Z or Z. So it includes negative 29, minus 5, 0, 222. All these can be called as an integer. And if we enlarge this set, we have ratios also included. Like you can see here, it would be 7 by 3 or minus 2 by 9, minus 5 by 4. All this would be falling into this category called rational numbers represented by q. Okay, so any number that you can see here within this box is a rational number. So 39 is a rational number, How? Because 39 can be represented as 39 divided by 1, or let's say minus 29. Minus 29 can be represented as minus 29 divided by 1. How about 0? 0 is also a rational number. 0 can be represented as 0 by 1. 0 is a integer, 1 is an integer, so we have the denominator 1, right? So we have 0 divided by 1. Now rational numbers do not have a unique representation in the form of p by q. So what does this mean? So there can exist equivalent rational numbers of fractions. So let us look at what is 63 by 42 and can we represent it in a different form, right? So if you see here 63 by 42, we can factorize it and write it as 9 into 7 divided by 6 into 7. Now we have 7 as common factor, right? So we can cancel out the 7 and write it as 9 by 6. So this is what is meant by rational numbers do not have a unique representation in the form of p by q. So it does not have a unique representation. That means a same number can be represented in so many different ways and it will all represent the same number. Okay. Further, if you look at 9 by 6, it could be represented as, or we could first factorize it as 3 into 3 divided by 2 into 3, and if we cancel this 3 and 3, it becomes 3 by 2. So coming again, when I say rational numbers do not have a unique representation in the form of p by q, what it means is that the same number can be represented in so many different ways. Like here 63 by 42 is same as 9 by 6 is same as 3 by 2, all is representing the same value on a number line. So if you represent 3 by 2 or 9 by 6 or 63 by 42, all will be the same point on a number line. So we can have, or there can exist, equivalent rational numbers of fractions. Okay. But generally when we are writing, it is always nice or beautiful to represent p and q with no common factors other than 1. Okay. So in other words, what we say, p and q are coprime. What are these coprime numbers? Come again. In general, it is always nice to represent this p and q, which forms the rational number, with no common factors other than 1. So 3 and 2 in this case, do we have any common factor different than 1? No. 1 is the only common factor we have between 3 and 2, and 3 and 2 or 2 and 3 together form a coprime. So when we reach this stage of factorizing, we have the simplest form or the smallest form of representing a rational numbers, and in general this is what we are interested, or there is, of course we can represent it in any way, but we will make our life easier, much important, we will make our calculations easier when we have smaller numbers.